Okay, I was hoping that Roger would be here. I don't want him to have any excuses at the quiz at the end when I start asking questions. I don't want to hear the excuse that he wasn't here and might have missed it, but anyway.
It's recorded.
I'll start off. So this lecture is about spectrum analyzers, which I've got up here. So it's an introduction to spectrum analyzers. So as an introduction, I've taken a few shortcuts because they are quite in-depth instruments and very complicated instruments nowadays. So as part of the introduction, I'm just going to be talking about what is a spectrum analyzer, what they're used for, how to operate one, and importantly, how to prevent destroying one. They are very easy to destroy, and many so-called professionals end up destroying them. And as Greg said earlier on, what happens is that people actually end up transmitting into them. They keep saying, I'll remember, never hit the press to talk when I got things connected, but they don't. So we'll launch into it. So what is a spectrum analyzer? So a spectrum analyzer is basically just a superhet receiver. That's all it is. That's basically all it is, just with a few little additional smarts around it. So it has a log detector and it has a visual calibrated display. So why are they so complex and expensive? And the answer is because basically of the calibration that they've got inside them. They are a calibrated instrument where most receivers are not calibrated, and the accuracy that goes along with that. So what does a spectrum analyzer do? So basically what it does, it processes an incoming signal and displays the spectral content of that signal. So you can use it for looking at, with one glance, the signal power, typically in dB, versus frequency. You can measure an unknown frequency. You can identify and measure an unknown frequency. You can visually look at the harmonic content of a signal, look for spurs. You can observe the spectral purity and measure the spectral purity of CW signals. You can look at percentages of modulation of AM, deviation of FM signals. You can identify noise, impulse, random, interference you can identify. You can measure field strength if you've got a calibrated antenna to go with it. You can observe and measure filter frequency responses, and you can measure intermodulation distortion. And that, as we all know, is it occurs when two or more signals are applied to the input of a nonlinear device. And spectrum analyzers can work from audio up into the tens of gigs easily range. So they're very, perhaps not in the same box, but they do cover that range. So some people use them just for audio use and look for specifically for distortion IMs in audio circuits, high-end audio. But we typically just use it for RF. So that's what I'll be focusing on in this talk. So I've got just a few snaps of some representative spectrum analyzers. I've went to a bit of pain to get some old ones, some new ones. So we've got some old beauties here, the old venerable HP 141, some more modern ones, and then a combination of desktop to sort of portable to really portable ones. So they sort of come in all sorts of flavours. You can see the older ones have got just monochrome CRT displays, and these ones are all just totally analog all the way through the circuitry. And the more modern ones, as you can see, have got typically LCD and colour displays. But they're all spectrum analyzers, and they all do much the same thing. And the next shot is a few spectrum analyzers from my collection, as well as the best SA spectrum analyzer. The best spectrum analyzer ever is that one there. Well, in fact, it's not. That's a joke. The best spectrum analyzer ever is Phil Angilli's.
Yes, I was going to say, expect to see a picture of that there.
I didn't have a picture of it. So this is an artist's impression. It's an artist's impression of what Phil's spectrum analyzer looks like. And for those that don't know, it's the best spectrum analyzer ever because many years ago Phil designed and built his own. And for many years he had it in a shoebox, which used to amaze us. The thing would be sitting in a shoebox working, but in later years he's actually made some metal compartments to put all the various...
So how did he fit the V8 engineers?
Anyway, so yeah, Phil's got the best one ever. You just got to take your hat off. So, spectrum analyzers. To try to explain them, you have to get your head around the difference between time domain and frequency domain. So, what this drawing is trying to display is a three-dimensional drawing with amplitude in this axis, frequency going away from you, and time in this axis. So if you look front on, looking into this...
Tim, do you just want to pause for a moment?
Yes.
We'll grab some more chairs. Take off, pause.
So in the time domain is what cathode ray oscilloscopes, CROs, look at. What you look at is the signal as it varies in amplitude over time. So with a CRO looking this way, that's what you're seeing. With many signals, they all appear as a jumbled up mess. In the frequency domain, you look at it in this axis. So you're looking at amplitude versus frequency. So this is these three signals. So you have three different frequency signals. If you looked at those three on a cathode ray oscilloscope, you're just looking at this jumbled up mess. If you looked at a spectrum analyzer, you would see the three distinct frequencies at these distinct frequencies. So that's what it means when we talk about the frequency domain. And so again, just looking at just some screen snaps of what spectrum analyzers look like. And again, this is what I was trying to explain. Amplitude is on this axis and frequency is on this axis. And we can see we've got two signals here and we have inevitable noise at the bottom here. So we've got, again, I've just grabbed a few different snaps. And again, the old CRT analog type displays versus some of the more modern displays. They all show the same thing, show it in different ways. So that's what a spectrum analyzer is all about. And if you have a look at these ones, you'll see the date and you'll see that these two I grabbed from less than a fortnight ago. And this is a spectrum analyzer in action. And what this was about, just very briefly, I maybe jumping ahead, but since I've got this slide up, I'll explain it. Many of us know Bruce from the club up in Queensland. He gets called out when there's intractable problems that no one else can solve. And there was a complaint that in a shopping centre, a radio network, an emergency services network, there seemed to be some odd problem that it didn't work. Didn't work, inverted commas. Everything doesn't work. What's it for? Doesn't work. Doesn't work in the shopping centre. So Bruce was called out. And he took his spectrum analyzer along, and what it was, this is a snap taken inside the shopping centre. We can see some carriers up here, which we can effectively ignore. So these are mobiles type carriers, cellular carriers. But what you can see here, which is centred from about 300 to 500 megs, is a whole lot of wideband noise. And so the signals that we were trying to look at were residing in here. So this is before, and then Bruce being Bruce, he hunted it down and found out it was being caused by a LED light in a shop. And once the LED light was turned off, bingo, there we go.
Is that on again now?
Sorry?
Shop's got a broken window.
So that's the use of spectrum analyzers. Without a spectrum analyzer, things like this are really hard to find. And I also should add that to hunt it down where it's coming from, Bruce actually used one of those sniffing loops that we built as a project here some years back with that blue hard line. Yep. So that's what he used to actually find out what it was. So that was just all of it one. It was wideband from about 300 to 500 meg. This rubbish. Yeah. We're just switching a regulator for a LED light in a shop.
Can you actually force the people to turn it off?
Well, we can, and we have occasionally done it if they're uncooperative. Yeah. But usually, Bruce being Bruce, he's very good. Yeah. And with most people, you talk to them and you explain to them, and they cooperate. But there again, if they don't cooperate, it's a simple matter. We've been in a position in the past we're forced to do it. We just hand all this to the ACMA and say, go sick 'em. And because of the network, they snap to it very rapidly and go and have a talk to them and say, you either turn that off or whatever it is, or we serve you a notice. What do you want? And so, we get compliance that way. So the ACMA are very good.
What frequency, what was the emergency frequency?
It resides in 420 to 430.
So it's, yeah, okay.
In the harmonised government spectrum.
Yeah.
Harmonised is the official ACMA words for it. Okay, let's move on. Spectrum analysers. There are two basic types of spectrum analysers. The first one I'm going to mention is the one that came second chronologically. This is a modern beastie, but I'm mentioning it first because I'm not going to talk about it ever again. These things are reasonably new, and so they use fast Fourier transform, fast Fourier analysis. And if you think about it's very similar to an SDR receiver nowadays in how it works. So what it has up front, it just takes a snap of all the spectrum, all of a sudden, all at once, the whole lot of spectrum, and then crunches it using maths. And so with microcomputers and all this nowadays, you can do this sort of stuff. And as the microprocessors and computers in these instruments get faster and better and more memory and all the rest of it, the functions and features of these things are getting better and better all the time. So if you want to have a look at this, so that's all I'm really going to say about it. So just think of SDR receivers.
So basically you can repurpose your software-defined receiver to do this, right?
You could, yeah.
You just change the software.
Yeah, you could.
Calibration.
Yeah, it's a calibration to kill a dealer, but yeah, you could. Yeah.
So your $20.
Your $20 one, probably not.
It'll do it, but about $20 well.
Yeah.
Not very accurate.
Okay, the second one is the traditional one, and is what I'm going to be talking about, which is called a sweat tune spectrum analyzer. So it's the one that's still most widely used, and it again, as I said up front, it's if you think about a superhet receiver, this is how these things work. But instead of just one receiver, it scans all sweeps. So I might just jump into this little bit. Here's a little tuning aid that I've got. So here we are again. So we've got the two axes. So here's amplitude, here is frequency. So when I say sweep, we have a filter, like in any old receiver. And what happens, this thing sweeps along. So here, nothing. Oh, signal. So that's basically it. So the thing just sweeps, just continually sweeps. And as it sweeps along, the sweeping is synchronised with the display.
So what sort of speed does it sweep?
That's variable.
Right.
Ballpark. It can go from a millisecond across the screen to minutes, tens of minutes across the screen.
Okay.
So Tim, does that just have a local oscillator that varies in frequency across the spectrum that you want to look at?
Well, have a look at the major building blocks are comprised of these things. So we can see, if we think about our superhet receivers, it's exactly the same. There's nothing really tricky there except for the display. Used to be monochrome CRT, but nowadays LCD. But all this stuff's exactly the same as what we see in the superhet. So that's it in words, and this is it visual. So your input signal comes in, goes into an RF attenuator, and then typically a low pass filter or some sort of pre-selector filter at the front end, then into a mixer, and the mixer's fed from a local oscillator which is derived from a crystal reference, and that's swept by the sweep generator. This mixer then has the input signal, muxes it down to an IA frequency, amplifies it, filters it, a log amp, as I said, this is the important thing, detector, then another filter, a video filter, and then it displays it on the CRT, which is kept in synchronism with the sweep generator, which feeds both this and this thing. It's a basic superhet receiver.
So why a video filter?
We'll get onto that too. Good question. We'll get onto it. I'll say here for the second time, and it won't be the last time, that if there's too much input signal comes here, through here, what happens is this front-end mixer gets destroyed. And as I said, these things typically go to gigs or tens of gigs, so just imagine how expensive this little baby is. They are incredibly expensive. So what happens? It happens over and over again that people accidentally transmit into it. This mixer gets destroyed, people go ask for a quote, and in the end they usually throw the thing out and buy a new one. those things are really expensive, and if a spectrum analyzer is a few years old, they're just not worth replacing. It's just too damn expensive. So if you think about buying one on eBay or whatever, if you think about buying a spectrum analyzer and you see the words "worked last time I turned it on," we know what that means. It means that if it still worked, I'll be keeping it and using it myself. So beware. Okay, let's move on to the IF filter. So the IF filter is just a little baby here, a little bit further down the track. I'm not going to talk about the RF attenuator or even the mixer. We sort of, we got a good grip on that from our normal. There's nothing tricky about those things, the normal ham stuff we do. The IF filter is very important, and I'll get on to that. But just briefly for the moment, what it's saying is that what we have here is, in fact, a variable filter. We can see it's indicated by the arrow through it. So it's not just a single filter, there are a number of different filters, variable filters, depending on what you're trying to look at on the output. And so we have the bandwidth, which are RBW, which we'll get onto in a second. And we can have various bandwidth filters. So again, think of your receiver. So here's Patrick with his CW filter in. And up here, here's Roger with his AM filter in. So the different bandwidths, as we know. Nothing too surprising about that. So the IF filter is a bandpass filter used as the window for detecting signal. So the bandwidth is also called the resolution bandwidth, RBW. This is important. So the first thing we learned about, which is important, is be careful how much RF you put into it. The second thing is to remember this, the RBW, the resolution bandwidth. And you can change it, adjust it by the front panels. All spectrum analyzers have a broad range of variable resolution bandwidth. And what you can do, like everything in life, there's a trade-off. So with any instrument, you have to trade off the frequency selectivity of the instrument, which is the ability to resolve signals, which I'll explain in a moment. The signal to noise ratio, and the measurement speed, the sweep speed we spoke about, which could be from milliseconds up to tens of minutes. And as you narrow the resolution bandwidth, you improve the selectivity, you improve the signal to noise ratio, but the sweep speed has to be decreased.
Does it do it automatically for you? Or
You can do it automatically. With old spectrum analyzers, no. The first spectrum analyzer that I worked on when I was at Jolly Old Perth Radio in 1980 was about the size of a bar fridge on wheels. And I wish I could find a photo of it. I think it was a Singer brand thing. It was a huge thing.
Singer.
Yeah. It was all full of valves, and yeah.
What's wrong with that?
Drift.
Yes, and it wasn't very well calibrated. You couldn't actually get a lot of calibration out of it. It was useful. It was the best instrument we had. It was very useful. But yes, if you had and had lots of settings you could adjust, and you had to make sure you got them all right, which was an art. It was an art. I won't go into it. So let's have another look at that one. So what we have, there's a signal we want to have a look at, and here we have, for the purpose of this demonstration, we've got two bandwidth filters. So there's Patrick's CW, and there's Roger's AM filter. So as the thing's sweeping across, and there is a signal here, as it starts getting into it here, we've got a wee little bit of the signal coming through. Not much, but a wee little bit of the signal. And as it goes on, there's more and more signal. So what's happening is this thing's sweeping along. All this is effectively noise. So with a wide filter, you get a lot of noise as the thing sweeps along until you finally get it within the centre there. As opposed to a narrower filter, as it sweeps along, there's a lot less noise as it gets into it, and then it sweeps and it's gone out the other side. The other way to think about it is, again, just think with your receiver. When you're trying to listen to a CW signal itself with a wide filter, as you know, you can hear all sorts of noise. You can hear the noise. So that's effectively the background noise, raised noise floor. And as you get the filter narrower and narrower, the noise floor goes down. So there's a few different ways of thinking about the same thing, just to see whether gels in your mind, different ways of thinking about it. So we'll demonstrate that. We'll come back to this one, but at the very end I'll do some practical demonstrations. But that's very important, the resolution bandwidth. This is where you can get yourself getting answers which are not right. So you have to be very careful about this. It won't destroy anything, but you get wrong answers. Just hold that till the very end. We'll come back to it. I'll show you in real life. Okay, so the next thing, just following the chain through, is the detector. So again, with modern spectrum analysers, you can select different detectors, not just one detector. So there's a couple of them there. There's a positive detector, so it'll in fact detect the largest value, or you can have a negative detector to detect the smallest value, or you can have a sample. That says last value, but a sample detector doesn't necessarily need to be the last value. A sample detector just takes one sample at random within that bin. And there are other detectors, but that's just some of them. So you can select different detectors, again, depending on what you're trying to do. And I think I'll leave it there. So the next one is, so this just talks a bit more about it. So you talk about the positive peak and the negative peak, which I spoke about. So again, with modern ones, with modern equipment, as you know, there's more and more processing of digital stuff going more and more towards the front end. So as they do that, just as these things get better and better, they can operate higher and higher frequency, go more and more the front end. Once you've got everything in the digital domain, you can do all sorts of tricks. All these detectors are just implemented within maths. It's all just maths. So when it's in the digital domain, it's easy to do. Okay, and this sample, right, just move on. Oh, the video filter. So, Phil, you asked about video filter. So there is another filter, which is after your detector, which is called the video filter. And it's a strange thing. This, you know, I remember when I first started, I couldn't understand what the word video had to be, but really all that's referring to is it's the filter before it goes to the video display. And all this does is clean the noise up on it. So if you've got a noisy signal coming out of your detector, if you put the video filter in, it'll just clean it up, clean a lot of that noise off it.
So it's photoshopping your thing.
If you like.
Video shopping.
If you like. And again, I guess that really should be drawn with an arrow through it too. There are various, I think all spectrum analysers would have variable video filters, so changing variable filters to give you different degrees of filtering.
You skip the login.
Well, yeah, but again, it's just a logarithmic amplifier. I don't want to draw this out and torture everyone having going for too long. So that's it. It's just a low pass filter, basically what it is. Just for cleaning up the signal and just smoothing everything off. And as an option, we can have a tracking generator. So a tracking generator may be included within the spectrum analyzer, and this provides an RF output via a separate connector. And so, as I've said there, the frequency of the signal that is generated from this output is in synchronism with the frequency that is displayed on the screen.
Synchronism, is that a new word? Or?
Isn't it?
Yeah, that's
Is it a word? I don't know. I wrote it there. I thought of it last night. I think it's synchronism.
that's all right.
Synchronised? Synchronism? Did I make that up?
Synchronism.
Yeah, that's good anyway.
Yeah.
Instead.
So in other words, the output signal tracks the display.
Or
And-
would we just be in sync?
Yeah, but syncs a contraction or something.
That'd be a user for you.
Synchrony.
Right, that.
Yes, okay. I remember you. What's your name again? When the quiz comes up. So this allows 2-port measurements. So up until now we've been talking about 1 port. 1 port on a device means just one connector. So up until now we talk about feeding a signal into it. With a tracking generator you can do 2-port measurements. So you've got an output port, which is a tracking generator, and the normal input port, which goes into the spectrum analyzer. So this you can use to sweep and tune cavity filters, sweep low pass filters. For instance, if you had a whisper transmitter and you got a low pass filter and you wanted to sweep it. You can do all sorts of strange things. You can find a value of an unknown L or C, inductor or capacitor. For instance, you can place your unknown with in series or a parallel with a known and sweep it and see what's resonant and then work it out, just things like this. If you have another box called a return loss bridge, you can sweep an antenna for a return loss, and return loss equals SWR. Just think of that, just not comfortable with the word return loss, think of SWR. And a return loss bridge looks like this, and I've given, that's mysterious, do that, will it? Yeah, okay. Okay, we'll leave it. Somehow or other, this one's gone underneath it. But a return loss bridge is a box, and again, this has got 3 ports, and a device under test, which is your feeder, let's say, going off to an antenna. So this RF input, you connect to the tracking generator output of your spectrum analyzer, and reflected RF output, you connect into your normal port of the spectrum analyzer. So the RF comes out here, and by the magic inside here, goes out to your antenna. Any reflected power comes back this way, and by the magic in the box, gets directed into the spectrum analyzer. So you can have a display looking at return loss. And the one that's disappeared under there was a Roden-Schwartz device. And why a Roden-Schwartz device? Because the Manly-Warringah Radio Society owns a Roden-Schwartz model FSH3 spectrum analyzer. And that's it here, which we'll look at in a moment. It is a battery-powered handheld unit, so in other words, it's really good for use in the field. It's portable. There are some inevitable trade-offs between portability and specifications. And the frequency range goes from 100 kilohertz to 3 gigahertz. And the model that we own, in fact, includes an inbuilt preamplifier and also a tracking generator, which is why I spoke about tracking generator previously. And the maximum input to RF being fed into it is plus 20 dBm. Plus 20 dBm is 0.01 of a watt. So for what's the third time I mention it now? Any more than that, it'll risk being irrevocably destroyed. So I might just move on to some practical stuff now. Let's have a bit of a look. We've had a bit of a theory. So I'll just ask Greg to swap his camera. We'll just pause that. Hot swap it, yeah?
Yeah.
Is that plug one a 2-port device?
Yes, it has a track generator, yes.
Yeah.
But not the return loss bridge, unfortunately.
Which you would need to analyse an antenna.
Yes. Okay, so up on the screen, this is it here. So this is the Roden-Schwartz handheld FSH3 spectrum analyzer, which covers from 100 kilohertz up to 3 gigahertz. And you can see a display on the screen now. We're looking at a signal which I'm generating out of a signal generator over here. And so if we have a look at that, what can we tell about that signal? What can we say about it? We can say, I'll just keep talking. This down here is, let's just say that's noise, random noise. Don't worry too much about that. There's noise is inevitable in every circuit. And we can see a single hump.
So is there any chance we can drop the front lights a bit? Just actually that would give us better resolution.
Can someone up the back there turn the front lights off, please?
It's all the lights in one shot, but yeah, we can try.
Okay.
Yeah, that's
okay. We've got this one here. So.
Oh!
Oh, lovely.
Hey. Who's that snoring?
It's our ghost story.
Okay, so what can we tell about that? Anyone want to take a punt? Anything? Nothing? Something?
Single hand frequency.
Single frequency, but is it? So I mentioned before talking about the resolution bandwidth. So in fact I've set this up so I can instantly adjust the resolution bandwidth, because as we said, everything's adjustable. So if you have a look at that, all I'm going to do is adjust the resolution bandwidth, which I don't know whether you can see or not. Yeah, you can't really see. Is this up there? It tells you what the resolution bandwidth is. So I'm just going to decrease it, and so I'll drop that down. Currently it's 3 kilohertz, and that's now down to 300 hertz. And so from that we can see. Can we?
Yeah,
Hope you can see.
Not really, but
There's two.
Two
Let's
humps.
do that.
you can tell.
Can we zoom in maybe?
Yeah.
Is that possible? Yeah.
It doesn't have a video output.
The spectrum analyzer has an optically coupled output, which is interesting. So it's absolutely isolated, and so it can be remote controlled from a PC, or you can output to a printer.
Okay, that's good.
Yeah, that's good. You can
Is that
see
good?
I'm sitting at the front.
So now what can we see? We can see previously we saw one big, it looked just like one signal, but by decreasing the resolution bandwidth and changing nothing else, it has shown us, in fact, what it is. That's in fact an AM modulated signal. So you can see a pair of sidebands there.
Yeah.
See the carrier and a pair of sidebands. So the takeaway message is be careful with the RBW, resolution bandwidth. When you're looking at a signal, be very careful. Make sure you've got your bandwidth set correctly, because you may miss what you're looking at. And just out of interest, since we've got it here, I might just try this as well. There's another bit of a thing which we've all learnt about, but until you see it practically demonstrated, it's difficult to get your mind around, which is this. Now, can people see that?
Harmonics.
FM.
Ah.
That's a function.
Yep, yes to all of that. So what we're looking at here, I've changed the modulation to FM. So this is in fact an FM signal, and what we can have a look at is we can see the carrier here is now dropped right down. We can see these other, what I call Bethel functions, or the other sidebands there, but the carrier has dropped down. So we learned about this. It seems such a strange thing with FM. By changing the modulation index, and I'll do it here, we can in fact change the carrier and make the carrier come up, make all those sidebands go away, just by very small changes in the modulation index. I'll just go back the other way. Just changing it slowly. Going through it. You can in fact, if I could do it gently enough, and make that carrier disappear altogether. So that's just about gone there. So it's an interesting thing with FM. You know, as we do our license, we learn about all the theory behind this, but I don't know about you, but until you see it in practice, it means a lot more when you can actually see it. Have a bit of a play around with FM. Just as an aside. Okay, next. So with the spectrum analyzer, we can do some other fun things. So let's just disconnect that antenna. And I'll use my pointer to connect the pointer into the input. And let's get rid of that. So down here.
Reading the screen with you, Tim.
Oh, buddy. Sorry about that, Chief. So if you look at the front panel of this instrument, we can see the most used buttons are quite conspicuous. So the ones on the side here. So this one here is called frequency, which I'll now press. And I don't know whether you can see, it's come up with some options here. So it asks you what frequency you want to scan across. So this one here, can you see that? It's having difficulty behind it. This one says the start frequency. So if I press that and I say 88 megahertz, and then stop frequency, if I go to 108 megahertz,
132.
going to that, and because I've open that up quite wide, we can now see that
Scanning very slowly.
yes,
It's
yes.
No, it's just going slowly. It's,
Because the resolution bandwidth is still down at the very low. So I'll just increase that. So I've got this up to 3 kilohertz now. So that's increased the sweep speed. So now what we can see there is, so 88 to 108 megahertz, what's that?
FM
band. So we're looking at the FM band here, and so what we are seeing are the various FM stations. So they're the carriers from the FM stations.
So what's the strong one there in the middle?
The strong one's there in the middle. Okay, what we can do is, this button here is called marker. So press the marker button, and it brings up a marker, which is off the end here. This thing here says marker. And then we can roll the marker along.
And where Tim's the
Or an easy one is to set marker to peak. It's not the peak, it's the next peak, but not the peak. Set marker to next peak, which is that one. Is that one you want to just look at?
Oh, no, we're seeing your back of your arm at the moment.
Yeah, sorry about that. Is that the one, Greg?
I think so.
101.3. Is what it's saying?
No, it's not. It's
Okay. So that's the strongest one we got here then, is the one on the Central Coast. So it's interesting that we can use these markers, and in fact we've got multiple markers if you want to. And so the marker itself is telling you what the frequency is. Again, it's hard to see, but up the top here, it's 101.3333333. Wouldn't pay too much account of that, of the so-called accuracy of the marker itself. But you can, if you wish, you can go into a separate marker mode, and there is an option for, which you can't see here, called frequency counter.
Right.
You can see that it's greyed out. So again, with all these, the benefits of these digital instruments, the benefit is that when you've got things digitised, you can do anything with it. The benefit from the manufacturer is that they can go, you can do anything with it, but we're going to license it. And so you have to pay us money to unlock all these additional functions that we can do. So all the features is loaded in this machine, and you pay the manufacturer money, and they'll give you a secret number, and then you can go into our menu, put that secret number into it, and unlock these features. One of the features is this thing with a frequency counter, so it has got quite an accurate, or a very accurate frequency counter in it. So instead of this 101.3333333, if you can enable that frequency counter option, it will tell you exactly what the frequency is.
So we need the Rode and Schwartz code packet.
Oh, we wouldn't do that. We'd pay the money. We're all honourable people here. So,
Can you demodulate the signal if you send the marker?
there is a pair of headphones here, and there is a headphone jack on the side. So yes, you can plug the headphones in, and if you go to zero span, so the thing's not sweeping over all the time, but sitting on that one frequency, you can in fact demodulate the signal and listen to it.
Expensive.
Yes, but again, if you're attracting any interference, sometimes that is very useful. When things are coming and going, you go, what the devil is that? And you can have a listen to it. It may not necessarily be voice or speech, but some of the common data type sounds, when you've been in the industry for a while, you can recognise. So control channels, MPT 1327 control channels, P25 control channels. They have a distinctive sort of repetition sound to it, and you go, oh, no, that one is. So it is useful. It doesn't sound like it is useful having a pair of headphones, but it is useful when you're hunting an interference. So there's a marker D mod. I think that's the way you do it. Yes. So there it is. So you've got off and AM and FM. I don't really can read it, but that's for demodulating with the headphones on the side. So that's just a very brief rundown of it. So we've had a look at the switches on the side, the frequency switch, the span switch. So with the span switch, we can go to things like full span. With full span, that's now sweeping from 100 kilohertz to 3 gigahertz, and you can see
What's happening on 40 metres tonight?
we could have listened on 40 metres tonight, but with this antenna and all the other rubbish around, probably wouldn't be able to see too much.
Oh, you will on
But again, see how
And that's less than 0.1 of a watt.
we can see how slowly that's spanning, again because of resolution bandwidth. So let's just speed that up, and we'll speed that up to 1 meg, and there we go. And we see how the noise jumped up. You know, we talked about when you change the resolution bandwidth. So I'll just do it again. I'll just decrease the resolution bandwidth, so you'll see this is saying 100 milliseconds. So it's sweeping in 100 milliseconds, and this is 1 megahertz resolution bandwidth. So this is 100 kilohertz to 3 gigs it's sweeping at the moment. So if I change the resolution bandwidth down, so from 1 meg now, I'll now take it down to 300 kilohertz. See how the noise drops down, and the sweep has now gone up to 167 milliseconds. If I take it down one more time to 100 kilohertz, the noise has dropped down and the sweep time's gone out to 1.5 seconds. So unfortunately, there's a trade-off. And the other button I haven't spoken about on the side here is this one here called Amplitude. And so this one changes the amplitude scale, so the y-axis scale. So what we try to do is not overload the front end, but we try to get signals of interest that we're looking at to be as high as possible. So at the moment we can see some signals sitting there. The highest signal that we can see is this one here. And so what we can do, zoom into this, we can change the reference level if we wanted to. Make it go to say 40 dBm. And it's done nothing. Reference level, minus 20. 40.
So Amplitude's adjusting the input attenuator, or it's just
Yes,
affecting the
yes,
screen?
it'll change things automatically. Yeah. So that's changed the top scale now has gone to plus 20 is right at the top, and so everything's been dropped into the noise. So we'll make it go the other way. So we can, if we say 30 minus dBm, now pushes it out, and it's now lifted these spurs up, so that these have come up higher in the screen, but we still got a lot of noise there. So now how to get rid of that if you wish to. We can change the resolution bandwidth. You can put it down. The bandwidth. And it scans slower, but the noise goes down. So it does other tricks. If you want to do save setups, we've got a preset here. If you press the preset, it just goes to factory preset conditions. But if you wanted to save all of the setup conditions, all those buttons the way I've got it set up now, you can save that. You've got multiple ones of those you can save and name and call back. If you're just doing, for instance, the same tests over and over again, it's sometimes useful to do that.
So you could save your let's scan the FM band.
Yes. Yes. Yep. As I mentioned, we have a optical coupler in here, so you connect the things up to a printer and print it if you wish to print that. And as you can see with those ones I showed you with Bruce's displays, that is sometimes useful to get those displays out of the machine and be able to email them instantly, which is very, very useful. You can control it with the computer, so you control this thing remotely. So if you wish, you could, for instance, with a lot of these more modern instruments, they've in fact got RJ connectors on them. You can just connect onto a LAN, give them an IP address, and can leave them just set up anywhere and just control them remotely, just to see what's going on. That's useful.
So it has got an RJ45 on
This one hasn't, but more modern ones do. Yeah, this one hasn't.
So you said this is a 2-port one?
Yes, this has an inbuilt track generator. I'll lift it up, you can have a look. I would lift it up, except this thing's sitting up. It's battery operated, so I can pull the mains out of it. And there it is there. So we've got the antenna ports, this one. So this is the antenna port on this side.
away from the camera.
Yeah. Got the light, but move away from the camera. And the generator output port is this one here. And there are other options. There's a strange connector here. There is a thing called a power sensor, so another box you can buy that you can plug into this, and it has an RF power sensor in it, and you can feed RF power through it, and it uses the processing power of the spectrum analyzer and the display, but it changes the display. It puts big numbers on it, so it will tell you,
How many watts?
100 watts, 5 kilowatts come on the screen. That's
So how do people zap it then? You said you've got to be careful to destroy it.
Okay.
So what scenarios?
So let's just plug this back in again and let's just have a quick look at this. So what people do is a couple of things. Number one, let me change the frequency here. So we'll go from start frequency from 100 megahertz. Stop frequency 150 megahertz. Amplitude. Just wind that down to around there. So, two things. Number one, people have a radio.
Oh, right.
Let's take a radio like this, and one of the advantages of who's doing that, someone beat me to it. Yes, very good.
You just get too close with a
Yeah, so either too close to it, or direct connection, like we had it connected before, so connected into an instrument, or yes, typically into a transmitter. People leave it connected into a transmitter and then actually transmit into it. I don't know why they do it, but I've seen it happen a number of times. As I said, people say, "Oh, I won't transmit. I remember not to transmit," but yeah, they do. So you can directly connect a transmitter, but you need suitable power attenuators to attenuate the power down into it, so you don't
Could you
destroy it.
transmit into a dummy load? Yeah.
And sniff off it.
Yeah.
Basically, yes. That's what you should do. Yeah.
So with what equipment we have, various bits and bobs, what might one use this for day to day? Sweeping antenna?
Without the return loss bridge, no. Next.
Okay.
How much is the return loss bridge?
100 kilohertz of bridge.
No, like practical.
Well, it depends on what sort of quality you want to get, and as you say, what sort of video. You just specified HF, so you don't want it in the microwave region. You can imagine. You want something cheap and nasty, 2 and 6. You want something that's accurate, calibrated, sweeps in the microwave region, thousands of dollars, and anywhere in between. We can make one yourself.
So can you use this to track down noise sources at home?
Yes, you can. Yes, indeed. Yeah.
Cavity tuning?
Yes. Yep. Next, any other suggestions? Come on, there's more uses. I gave you some up there before.
Entertaining radio.
Could you for fox hunting, for instance? Even. I'll just connect it back to here again. Because.
He's got.
No. Coming to a couple of things I wanted to show you. remember when I first connected up there, we saw the vessel functions? I just
Is that a vessel function?
what happened?
So we turn the record off on the camera.
Okay, I'll give you.
Vessel function.
Yeah, that's done. Okay. No, I just had, I don't know. Had a table of vessel functions. That's not a big deal. Can we get the lights back on there? Because this is sort of come to the more or less the end. The only other thing was at the end of a presentation, it's somewhat traditional to have questions. So I'll ask the questions.
How does it all work?
So now we know where that snoring came from. That's that giveaway. No. Anyone got any questions? That's very brief. I understand it's very brief. But what I really, sorry, I'm now it's a question. I'm going to keep talking. Sorry. Just hold that for a moment. So more than happy. I'd really like it if now next week people started bringing stuff up and we can sit down and go through it and do testing with people. That's what I'd really like. Sorry, Richard, yes?
The cavity, you have the cavity up behind you, you were going to...
Oh, yeah, I was going to do that, but it's a bit hard to see on the screen, so
Yeah,
I'm not going to do it. I might do it later when we stop.
Mhm.
Yes?
Why don't they put a switchable, pluggable mixer, so when you break it, you just change it, put another one?
Look, because it's calibrated and because it has to work into the gigahertz range, you need to keep the things as short as possible. Connections, not that good in the gigahertz range. So everything's all surface mount, single board, surface mount, very specialised ICs. And it's a bit like, spare part with cars, isn't it? It makes revenue for the manufacturer by selling spare parts.
Selling used. Actually, my license 27.
Plus, the mix is the most likely piece that you're going to destroy. They make their money out of spare mixers.
Other questions? Come on, there's going to be more questions.
So that's it. Oh, sorry. No, I just hear people say that things like inverters from solar panels and noise.
Yes? Yep.
So if you had a suspicion that, you got a lot of noise, like
Yes.
I've got S7, S8 at home.
Yep.
Can you sort of try and say, is it the solar system
Yes.
or is it the
Absolutely.
LEDs or what?
Yes.
That
Yes.
you can do that?
Absolutely, yes. So, with a spectrum analyzer and some form of antenna, it can be just as crude as just a bit of wire shoved in here.
Yeah.
Or, as I mentioned before, we had a project a couple of years back. We made some shielded loops out of hardline for tracking down noise. But yeah, sure can.
Switch off the sun and see if it goes down.
True enough.
Not sure.
Yeah.
what
Sorry,
sound
Bill?
switch
Just one comment. It's separate from the analysis. In some of the receivers now, we've got this thing of transmit Ethernet over 160 kilometres with about 3 megabits per second on a 900 megahertz ISM band. They're actually using Spectrum Analyzer live to analyse this chirp spread spectrum, to analyse each frequency, and it applies an individual noise blanket to that frequency if it sees something's dynamically using a frequency. So it's actually a real-time spectrum analyzer analysing the entire band and applying noise blanking so that you can
But
increase...
where is that device that's making the decision? Because if you're talking about over more than 100 kilometres long, you can't just have it at one end because it might be signals at the other end.
Yeah, well, so you must know what... It's changing 10,000 times a second. It's very, very fast spread spectrum, but it's actually analysing the band and applying noise blanking to any individual spot frequency which is noisy in the band.
Yeah,
Yeah.
it's amazing, isn't it? It's really amazing.
So it's sort of like an active thing
Once
as
it's-
opposed to
yeah.
just analysing.
Yeah, once it's in the digital domain, just throw a heap of maths at it, a lot of
Yeah.
power,
Yeah.
do the crunching, and then act accordingly.
Yeah.
Yeah, interesting. So is this commercially available or just in
Yes,
the lab?
yeah, no, commercially
Okay.
available, yeah.
Oh,
Oh,
thanks.
yeah.
Okay, so yeah, this is wonderful. Very simple thing to make and very good for tracking down interference.
What's the benefit of it?
Shielded loop. Well, yeah, not so much directional, but it only is affected by the magnetic component. It's shielded from the electrostatic component.
So does that plug into the spectrum analyzer?
Yes, yeah.
So is it fair to say that only works really in the near field?
Oh, yes, more or less, yes. It's quite insensitive, so you have to be close, which is good. You don't want a sensitive, amplified antenna when you try to hunt down noise, typically. You want to be able to get, when you get close to it, as you know from things like fox hunting, that's in fact one of the problems, that when you're close, you get too much signals, it's hard to find.
So the specs on the fast Fourier transform ones mustn't be as good if they're still using this sweeping technology.
They're getting there. Again, it's horses for courses in terms of operating up to tens of gigs. They're not there yet with them, but they will. Just as every day, the process is getting better and better and more powerful. So yeah, they're getting there, but yeah, that's the main disadvantage. Is the high frequencies.
So MITs are trying to perform it all in software
Yes,
rather than in discrete filters.
just doing the analog mode, to bring the whole block and transferring it down to an IF. Yeah.
So it all depends on the accuracy of the analog to digital converter in the first place.
Yes, but I think the A to Ds are very accurate nowadays. They can get really accurate A to Ds.
Sort of 24-bit.
Yeah, 24-bit, high bit. Yeah, makes them more accurate.
Tim, I'm sure we'd all like to have one of these units. What would be the approximate retail cost?
Well, yeah, again, because there's such a wide variety of them, but certainly a decent one like this fella, we're talking in the thousands of dollars, which is, this one was purchased second hand.
I think I'm not sure that I remember correctly, but the HPSDR project, the AD converter in that receiver costs something like $250 just for the chip, right? And the rumor at the time was that the U.S. Defense Department was buying ADD converters for their software-defined radios. They were paying $40,000 a chip, okay? But they were getting better performance.
You sure? Well, they just said to pay more.
Slightly
Well, both, probably.
a few more discrete bits.
Yeah, more bits.
Okay, interesting.
So you can get as much as you want, you just...
Need to pay for it.
Yeah.
Wow.
Very good.
Okay, if there's no more questions, that's it. Thank you much for your time. Thank you.
Thank you, Tim.
Very interesting.